Hello and welcome. Eamonn Darcy is my name. I'm the founder and operator of QEQA, the Quantum Education Centre of WA. And it's my pleasure to bring you lesson 2 from our 10 by 10 series, which are 10 10-minute free video lessons on quantum computing. And today we're going to talk about entanglement, probably the greatest quantum mystery that there is. So let me start my laptop, and the 10 minutes starts now. Okay. Well, again, I'd like to put it all into context, and Jeff Bezos does this as well as anybody else by saying quantum computing is the future. I am not exaggerating when I say it will change everything. And he is right. And if you thought it was weird in lesson 1 with superposition, that's where a quantum particle, a particle smaller than an atom, can be in many, many, many states, an infinite number of states actually, at once. And even more mysteriously, when you observe it or measure it or look at it, it actually becomes a particle, becomes a state, one quantized state. So that was amazing enough, but wait until you hear about quantum entanglement. Now there's a explosive graphic. Now quantum entanglement means that with subatomic particles, I could take 2 out of your body theoretically, entangle them, and then I could put one on the moon and one here on Earth. And if I just move the one on Earth a little bit to the left, the one on the moon immediately moves a little bit to the right. And that happens every single time. And no one really knows why. And Einstein didn't like it because this happens instantly. So some communication is happening faster than the speed of light, 8 minutes 15. So let me ask you a question. Entanglement's a big part of quantum teleportation, and that's where we can actually teleport a quantum particle from, let's say, Earth to an orbiting spacecraft. And we really think that this is theoretically possible. So I'm going to ask you a quick question. You can just answer to yourself or in your mind. When do you think we'll be able to do this? When we'll be able to send a quantum particle, the actual particle, or the information of the particle, 100,000 kilometers instantly. So there's no lapse in time whatsoever. So when do you think we could send it from the Earth to an orbiting spacecraft? In 10 years? In 50 years? In just 100 years? Or it's something that we'll never be able to do? Well, I'll give you 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Well, we've already done it. It was done. The Chinese teleported a quantum particle from their laboratories in Tibet to an orbiting satellite called Messius in 2016. Isn't that amazing? And that's all down to quantum entanglement. 6 minutes 35 left. I'm just showing you this because this is the quantum code for entanglement. I'm not expecting you to understand it. It's actually a Hadamard gate followed by a CNOT gate. I'm showing this because it shows there's only 2 very, very basic quantum gates, being the Hadamard and the CNOT, that you learn. When you learn quantum gates, these are the first 2 that you learn. And you apply these and you can entangle 2 quantum particles. It really is amazing. Now, what is really going on though? As I say, Einstein didn't like this. Now, Einstein's the one on the right, I'm sure you know that. And he didn't like it because something was happening faster than the speed of light, which sort of means that it goes against his general theory of relativity. So he didn't like it. He called it spooky action at distance. He actually said, look, there's nothing crazy going on, even though I admit it's spooky. He had to, because basically it happens. You know, this has been done 100,000 times and it's never ever failed. It always works. You change one quantum particle and the other one, separated by however far you want, will change likewise and instantly. And he said, it's not a case of that, it's just a case of there's a hidden variable. And he wrote a paper, I think it was in the early 1930s. He wrote a paper, it's called the EPR paper, Einstein, Podolsky, Rosen. And they were basically saying there must be a hidden variable in the quantum particle that we just don't know what it is yet. It's a bit like a pair of shoes, you've got a left and a right. And if I put one on the moon, I could separate them and put one on the moon, and then I could look at it on Earth and I've got a right. I immediately know that the one on the moon's a left. And that's what people believed for 30 years, until this wonderful man on the left, Professor John Bell from Northern Ireland, he proved mathematically that the hidden variable could not happen. He proved that the properties of a quantum particle only come into being when they are measured or observed, like in the double slit. Before that, they exist in a superposition. He didn't prove it was a superposition. He just proved that at the moment of measurement is when the quantum particle gets its property, whether it's spinning to the left or the right. And that is, you know, absolutely amazing. 3 minutes 15 left. I just wanted to mention the delayed choice quantum eraser experiment. It looks complex. It is a bit complex. But basically, this was done in 1999. It's only 23 years old. And what it was, remember the double slit that I showed you last time? This is the double slit with entangled particles. So we're adding a level of complexity in. What I want to tell you is that somehow the entangled particles, as I've just mentioned, always show the same property. But what happens in the delayed choice? One of the particles has to go through a heap of mirrors and beam splitters. Don't worry what they are. It just means that it has to go further to get to the detector than its entangled partner. Yet, the entangled partner gets to its detector first, yet it always correlates with the second entangled particle. How can that be? How can the first one know what the second one is going to end up with? Because these maze of mirrors and beam splitters, they delay the experiment, and they basically, it's a 50-50 decision, yet they always get it exactly right. It's as if the second particle is somehow going back in time and altering the reality of the first photon or electron. It doesn't matter which one you do it with. Now, this is showing that something strange is happening, but it does seem to indicate that events that have already happened can be altered in the quantum realm anyway. And we're all made of quantum particles, remember. So look, it's really exciting. I've got a minute left, and I think I'd like to spend that minute in saying you've now had a quick 10 minutes on superposition and quantum entanglement. What quantum computers use these two incredible forces to do incredible computations, because not only can they relate to being in many, many states at once, they can also have a relationship with another qubit, is what we call them. So you've got a bit in digital computers and a qubit in quantum computers. And the qubits can be entangled, which means that they automatically give the same result. And I'm out of time. I hope you've enjoyed that. Next lesson, yes, I can hear the clock going off. Next lesson will be on quantum mechanics, the interpretations. And this is unbelievable. Things like the many worlds theory of Hugh Everett, and the Copenhagen interpretation. So we know strange things are happening. The interpretations try and work out, hey, what's really happening? Thank you for your attendance. Please like the video, subscribe to the channel if you haven't done so, and tune in for the next lesson. Bye now.